Okay, great. Okay, so we're recording. Guys, quiet, please. Thanks. All right, awesome. So I'm just going to go through this, and this recording I'll share later today or tomorrow, but some of you could watch over the weekend to help you study or help remind you, hey, how do I do these problems, right? If you get stuck. So this is for you guys. And then you guys will practice on the hallway. So scores on a university exam are normally distributed. So this is chapter 3 stuff about normal distribution. You're given the mean and standard deviation. So, Yamar, I could do your wellness check in a little bit. I have to check everyone's wellness checks. Yeah. Oh, I'll just check right now. And I guess it actually is on.
Yeah, she just wait.
Okay. Then I have to change attendance. Hold on a sec. Let me pause. All right. So the mean is 68. Standard deviation is 9. In what range do you expect to find the middle 68%? Well, we do know that the middle 68% is within one standard deviation. So you could just actually just do this. You could say, hey, well, 59 is simply, excuse me, 68 minus 9. 77 is just simply 68 plus 9. So you don't really need to use a calculator for number 1, because you know that when the middle 68% is within one standard deviation. So there's really not, you don't really have to do that if you don't want to. If you wanted to, then what you would do is you go to the calculator. You go second vars, inverse norm. You want the middle 68%, so do 0.68. 68 is our mean, our standard deviation is 9. And then we're trying to find the center here. You guys may not have that option, but you'll see it says from 59 to 77. If you don't have that option, then what you would do is you would do point. So middle 68%, so it means that you want 16% to the left. So 0.16, so you have 60% each side. So you want 60% to the left. And it will give you the lowest number, which is 59. And then if you do it again, but in this case, I want 84% to the left because I want the top 16%. So you do this, but honestly, just know the 68, 95, 99.7 rule. And you see it'll say 77. So that's how you could use a calculator for that one. For number 2, what percent of scores are between 68 and 95? Now let's use a calculator for that one. Again, if you know the way the normal distribution works for the 68, 95, 99.7 rule, we could just do this. You can just use a calculator instead. So if your lowest is 68, your highest is 95, standard deviation is 68. Sorry, mean 68, standard deviation is 9. That's 3 standard deviations away from 68 when you look at 95, because the difference of 27. So it's about 49.7% or 49.9%. So it's almost most of it. So that's that one there. And then lastly, what percent of students score lower than 50? So 50 is 2 standard deviations below the mean. But what you could do again is go back to the calculator, hit second vars with option 3. And since you want, you want percentage, option 2, my bad. So you want to be less than 50. So it means that I'm going to keep the lower as negative 199 because I want to go further to the left of 50. That's 68. That's 9. Paste this guy. Yeah, you get about 2.28%. So that's how that works. 2.5, close enough. All right, next up for volume. Volume of oxygen consumed while a person is at rest, blah, 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 whatever. Bottom line, this is a scatter plot. Usually what you want to do is kind of imagine how the best fit line would look. That's the best one that goes right through the middle of the data, right? So first off, what is the response variable? Response is always going to be X, explanatory is going to be Y. Why do we call it that? Let's think about Trump, voting for Trump, and getting COVID, right? We talked about this. If you voted for Trump, we saw that there was a correlation that you might be more likely to get COVID. Does that cause it? Not no, because you probably didn't wear a mask, probably didn't get a vaccine, but it just so happens a lot of Trump followers don't get vaccines, don't wear masks, right? Just we see this in different states. So voting for Trump was X. That's the explanatory. Getting COVID was Y. That's the response. So I'm using how you voted in the election to explain the response that, oh, I got COVID because I voted for Trump. So yeah, go ahead. No, X. Oh wait, no, those two different volumes. It's really hard to read. So rest is X. Volume at rest. And so explanatory is X, and that's rest. Yeah, it's really let me get a highlighter out because it's a little hard to read. I didn't, gosh, those are really close too. Yeah, right. So yeah, oh, I got mixed up. You're right. Thanks, Luke. No, I did get mixed up. You're right. So explanatory is X. So if I highlight it carefully, yeah, thanks, Luke. I did get mixed up. Yeah, there we go. And then for response, that's Y. We'll use a different highlighter. So that's while running. Really hard to read, but that's running. There we go. So yeah, thank you. So in this case, what we're comparing is the volume of oxygen you consume while resting. Can that explain the volume of oxygen you consume while running? Okay. So that's what's happening there. And is it reasonable to consider a cause relationship? No, we never say that something can cause something else. We could say it's correlated, but you never quite say that. So yes, there's sometimes that suggests cause, but again, correlation is not causation. You want to be very careful about that. Now, when you're asked to describe the relationship, excuse me, you're going to usually ask about form and the association. So first of all, form is going to be basically the strength of the correlation, which looks strong. So you say the form is strong. And then the association, of course, is positive because there's a positive slope. So that's more like the slope. So that's what we're kind of saying about that one. And actually, if we go back to our notes again, our notes, so definitely set your notes, which are right here. Yeah, so basically you're looking at like how tight it is and then the direction. So that's really the two things we kind of care about. And the form, of course, is linear. We know that. So anyway, so it's definitely a line, positive slope, and looks pretty strong. So let's keep moving here. Okay, going back to normal distribution. So if we think about what's happening here, so you have a locomotive that uses some adhesion, whatever. Okay, that'll be fine. The need is 0.37, standard is 0.04. So what percent of adhesions are between these two numbers? So you could just use normal CDF again. I won't do all of them because that takes too long, but just show like number 6 again. You would just do this. Second vars, option 2. The lower is 0.35. The upper was 0.45. The standard deviation is 0.37. Sorry, the mean was 0.37. Standard deviation, I think, was 0.04. Let me double check all that right there. Come on, here we go. Yes, I got that all correct. So go back to the calculator, we paste it. See, it says 0.6687, and that's what you report as your answer. That's all. Pretty easy. You can use a decimal or percent. I don't really care. They're the same thing. Number 7 is like what adhesions are more than 0.4. So I probably would put. I'm not sure why they put 0.53. That should actually. That seems weird. I would just change that to actually 1E99. And then here, yeah, you want to be less than 0.333. I would do -1 E99 just to be on the safe side. And then of course, if you want the 9th percentile, that means you want the top 10%. You want top 10%, but you're going to the left, 9% to the left, so you put 0.9 and your mean and standard deviation. Luke, do you have a question? I don't know. It's just something that belongs. It's something you measure on the locomotive. I don't know.
Oh, it's just for this only.
It's just for this particular. Yeah, it's not a stats term. Don't worry about that. It's something that they want to measure for a train. Okay, next one here. I actually do remember this election quite well. For each of the 50 states, recorded percent of voters that voted for George W. Bush, who was president during 9/11 and the war against Iraq. In 2004, percentage voted for him in 2000. Actually, I do remember in 2000, I did not vote because I thought voting was not really worth my time. And I changed my mind because that was an awful, that went all the way to the Supreme Court and George W. Bush won. So yeah, so after I've always voted, I was like, I need to vote because these elections are way too close. And you should anyway, regardless. Anyway, you can see that if you voted for George W. Bush in 2000, most likely you voted for him again in 2004, even if you're upset about the war and all that stuff. Subscribe relationship, it is definitely linear. It's definitely positive slope, and it looks very tight. Like that if I draw a best fit line, it's really tight. Then it says if you remove the outlier, will the correlation change much? So the outlier is over here. That's probably the outlier because it's really far off compared to the rest of the data. So if I drew the best fit line again, actually, let me draw 2 different lines. Let me use a straight line here. So it's kind of hard to tell, but like if I just focus on this data, you have this, but let me do a different color. If I try to include that outlier, it's probably more, let's go straight again. Probably more kind of like that, I'd say, if you really want to kind of include that outlier. So I'd say when you don't include the outlier, it becomes less steep. So that's kind of what I would anticipate. The correlation coefficient should actually improve if you do remove the outlier. I'm not sure why it says the R value would decrease. Actually, it should increase. That's actually incorrect. It should increase because it's becoming more correlated. Stronger correlation without outlier. So anyway, let's keep moving. Number 12, research states that bone density was negatively associated with age. What does this tell you in general about the bone density of younger women? So if you're young, you probably have higher bone density. So if the age goes down, bone density goes up. And vice versa. So that should be pretty straightforward. 13, 14, more of the same stuff as before. Just use your calculator. You're given all these different mean and standard deviation, but just in the context. So this is my mean, that's mu. That's my sigma, that's my standard deviation. You're told you're underweight if you're less than 32 ounces. So to be underweight, that means that I do need to go to the left of 32. So this should be -1 E99. That's what we usually do. You find 7.66%. So here's your normal distribution. Here's your mean at 33. Here's 32. You want all this, right? And that's 7.66%. And then if you want to be overweight, apparently you're overweight for your top 5%. So you want to find the 95th percentile and what's to the left of that. And you'll find that's going to be the number there. Use the inverse norm for that one. That's second bars, option 3. Okay, keep moving. More scatter plot stuff. And just in the interest of time. Okay, we'll move this a little more quickly. For this stuff here, what's going on here? Again, you have a scatter plot. So give a positive value for the correlation coefficient. This is really strong. So it's not gonna be 1, don't say 1 exactly, but like you can say 0.8 or 0.9. It's kind of a ballpark estimate. Remember, correlation coefficient goes between -1 and 1. If it was a bunch of dots like this, then you would say close to -1 or -0.9 or -0.8. Suppose we change this from grams to ounces, and there are 20.35 grams in an ounce. We expect correlation coefficient to change. The answer is no. That's because R is unitless. That should not matter at all. No change at all. So the answer is no. For 17, a study found a correlation of -0.61 between the hair color of a worker and his or her income. Well, first of all, that's weird. Hair color is not quantitative. So I'm not sure how you would actually do that. Yeah, how's it quantified? So, yeah, no idea how that was found. That's just weird. I have no idea how that was found. So just know it has to be quantitative, right? Let's keep moving. Here, they want to do a scatter plot for the data above. So real easy, just have to kind of look, kind of match it up. We see that the higher your creativity score, probably the higher your sales growth. So you're more creative, you just sell more, I guess. So it's probably gonna be a pretty positive correlation. So I don't think it's gonna be the last graph. I probably, gosh, this is really hard to read. If you have 18, you're at 111. Okay, they kind of all show that. If you're at, let's see, creativity score of 7, you're probably at 89. Okay, those are all just, yeah, I'll make sure they're not, they're almost like 3 of them will kind of look the same. I'll make sure it's more obvious. But yeah, it's just gonna be that one. So anyway, we'll keep moving. More of the normal distributions, more of the same. And by the way, the real test is not gonna be this long. It's much shorter, just so you know. Yeah, just use your calculator. That should be pretty easy. But here you have to be just a little mindful that you care about, that you do make sure that the units match up at the very least. So they say that the time it takes you to type some sort of a thing they have to do. The means 20 to 30 minutes, standard is 20. You'll definitely be hired if you can do in less than 100 minutes, because that's a good thing. So what proportion can do under 2 hours? Well, 2 hours, 120 minutes. And by the way, you want to change this to -1 E99. And then if you want to be automatically hired, you have to be under 100 minutes. So -1 E99. And then they say that there's a cutoff. The slowest 40% don't get hired. So that means that high time is not good. You don't want high times. So obviously you want 60% to the left of 40%. You find that, and so if that's your time, you're just too slow. Another scatter plot. Here to asking you, how would you describe the strength relationship for each league? So this is the American League and National League. Gosh, it's kind of hard to read. It seems that the more home runs you get, the more stolen bases you get, I guess. So it seems like they both have a positive association. It seems like one is tighter than the other. Trust me, I'll make sure these are easy to read. Not gonna do anything on density curves on our test, but just so you know, what makes this a density curve? The area equals 1. So we see you have 1/3 times 3. And then between 1.5 and 2.5, that's a width of 1. So 1 out of 3, or 33%. Z-scores. Remember, Z is going to be the measure of how many standard deviations you're above the mean. So it's your data point minus your mean over sigma. So positive Z is good. That means you're at the high end. Negative Z means you're at the low end. So if you got a 2.7 Z-score, you're going to be super pumped up. Negative 2.1, you're going to be quite pissed off, not happy. And negative 0.1 means you're right in the middle. So. And lastly, for this here, to derive Z equals 0, that's 50%. To the left of Z equals negative 0.47, you can use your calculator for this. What you could do is assume when you have Z scores, you could assume that mu is 1 and sigma is 0 because it's standardized. So and you can make like the far left like negative 1e99, or the far right you can make it 1e99 if you're going to the right of something. And if in between, just use normal CDF. That's your lower, that's your upper, and use 0 and 1 for mean and standard deviation respectively. So, okay, so you have this as a